when 0 is transmitted, y is being 0 is being received, 1 is being transmitted, 1 is being received. So in that case, the channel capacity here is 1 bit per channel use, 1 bit per use. So every time I use it, I know 1 bit is being transferred. Okay? Right? So if the probability P is half, it becomes a problem because it just means that you can't really know what is being sent, because the probability of receiving 1 and 0 is just become random, right? Right. So it becomes the channel capacity for that special case when noise becomes dominant, then this channel cannot be used, right? It's useless. Okay. 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 But just remember, this is channel per use. I mean, it's per use, right? It's still not the one that we are interested in. So what we are probably interested in for engineering purposes, we are more interested in beats per second. Right? In terms of capacity of the channel. So the special case for the channel is this called additive white Gaussian noise channel. So additive white Gaussian noise is that, let's say this Y is what you're going to receive, this is what you send, and then in the channel there's this noise that's written as N. Right? So in digital transmission, we are transmitting bit by bit, right? So it's a discrete time. Right? So every time we transmit, we are using the channel. Right? So you can kind of understand when I want to transmit per channel, it has to be related, when I change the channel capacity to bits per second instead of per use, it has to be proportional to the bandwidth. Right? You understand? Because the higher the bandwidth means that the more time I'm going to use the channel, because these are discrete channels. Alright? Okay? So it's proportional. So when we convert our channel capacity previously, this is only per use of the channel. Now in digital transmission, I'm using it per second, right? And how much I can transmit per second depends on what is the bandwidth that I'm using. Okay? Remember, we relate the bandwidth to how fast the signal can be transmitted. If you want to transmit very fast, it means that you want to attempt to transmit very fast. It means that you need a larger bandwidth. And in most of our case, where in wireless communication for application purposes, we are always limited. We are always transmitting through a limited bandwidth, right? So we are so capacity is kind of limited by the bandwidth, right? So this is one thing. And then the other thing that is not so well known, not so obvious, which we are not going to derive, is that this gamma, I think, is also another way of writing is the signal to noise ratio. Right, sometimes I think in the earlier slides you will see that this is written as C equals to bandwidth log base 2 1 plus sigma over n. Right, so this is written as 1 plus sigma S over S, signal to noise ratio. You know what is the signal to noise ratio? So in our additive Gaussian noise, right? So if you look at how in the frequency domain. A Gaussian noise is actually has a noise at all frequency level, right? So then our signal, our bandwidth, is something like this, right? So the signal to the noise ratio is this is what we're referring to. How much signal we have compared to the noise. And noise is something that we can't eliminate because of thermal energy, right? We live in finite temperature, so everything will have certain noise, and this is noise that we can't avoid. This is the what we call the additive Gaussian noise, which is kind of idealized noise because it can be used for calculation. And you kind of sense that the SN ratio is kind of a way where it's related to our error probability rate. It's related to this, right? Because the higher the signal to noise ratio, the lower the probability of detecting error. So we didn't go through the full derivation of how we reach this, but you should have a sense like where we get our channel, which is the information per use, how we derive that. So it's dependent on what is the probability error, right? And then once we have that channel capacity, then we need to multiply by a certain bandwidth, because the larger the bandwidth that we use, we can use this channel more often. So the final capacity that we are interested in, or we want to know, is finally this is, which is in terms of bits per second. Right, so if you look at this equation over here, right? So obviously we know that if we want to transmit at higher theoretical data rate, I need to increase the bandwidth, right? That's one. Then the other one is that I need to increase my signal to noise ratio. Assuming noise is something that you can't control, then we need to increase our transmitting power, right? So, but for mobile devices, there's a limitation of how much power we can transmit until people say that it's not safe anymore. So that is the limitation. And then there's the other limitation is how expensive. I think bandwidth, in a way, is being translated to how expensive it's going to be, because we have a finite bandwidth, right? And the government will always auction it off to the transmitter. So it's